students, welcome back to Chemistry Online class. Today we are teaching a very important topic in chemistry, and that is entropy and spontaneous reaction. What is a spontaneous reaction? A spontaneous reaction is a reaction that occurs with a very low energy or that requires little or no energy at all. A very good example is roasting. It takes place even without us, without human beings trying to add energy or aid the reaction. Most times we just notice a metal exposed to the atmosphere. After some day, the metal would have changed color to a brown substance, a brown metal, because of the appearance of iron 3 oxide. It has also undergone oxidation reaction because of the exposure to moisture, which is water vapor in the atmosphere, and oxygen in the atmosphere. So that is an example of a spontaneous reaction. It does not require our own energy. It doesn't require any other external factor or much energy or catalyst before it occurs. So it means that for a reaction to be spontaneous, that the free energy of such reaction must be very, very low or negative. So it means that if a reaction is positive, if a reaction is not spontaneous, the energy is definitely positive or high. Now, what are the conditions for a spontaneous reaction? We have a chemical, we have a shortcut here that we can use to actually determine if a reaction is spontaneous or not. Now, this G here, the change in G here, represents change in free energy. That's G's free energy. Now, H here represents enthalpy change. Now, enthalpy change or enthalpy itself it means the heat of a reaction. That is the heat involved in a reaction. And it also determines if a reaction is exothermic or endothermic. I'm going back to that later. Now, T delta S means, T here means temperature. And the temperature must be in Kelvin. It must be converted to Kelvin. If it is in Celsius, you must add 273 Kelvin to it to get it in Kelvin. And then this change in S is actually the change in entropy. Entropy. And so what does entropy represent? Entropy is a measure of the degree of disorderliness or randomness of a system or of a reaction. The entropy is usually higher in gaseous state. When a reaction is in gaseous state or is changing from liquid to gaseous stage, the entropy or degree of disorderliness increases because the particles in gases are usually in a constant motion, and so the particles are not free. The particles are free. They are not at a spot. They are always moving. Definitely, the entropy in such kind of reaction will be higher. So entropy is higher or positive in gases and lower in liquid and even the least in solid. So for a reaction involving a solid phase, the entropy is expected to be very, very low. And so for a reaction to be spontaneous, using different value, I'm going to assume different values here. I will use different values to represent these parameters, and then from there we'll determine what G represents. If delta H, that is the heat of reaction here, is negative, that is an exothermic reaction. If delta H is negative, which involves an exothermic reaction, like minus 50, and then you have minus here. If the temperature here is like 10 plus 273 here, or let's say both the temperature and the entropy, by multiplying the two together, we were able to get 5,000 here, multiplying the temperature in Kelvin and entropy change, because between T and delta S there is a multiplication. Now, having done this, by the time you open bracket, you're going to get a negative value here, minus 5500, minus 5050 kilojoules, which is the free energy. Now, if free energy here is negative, which is as a result of the fact that the delta H, that's the enthalpy change, is negative. It means G's free energy will be negative. And even if the enthalpy is not negative, if it is very low, that's delta H here, like 50, minus 5,000. If enthalpy change is negative and the total of, or the product of temperature and entropy is higher, or temperature is higher, or the entropy is higher, by multiplying the two together and subtracting it from a lower enthalpy, we will definitely get a negative value. So with this, we can determine if delta G will be negative or positive. So delta G, which is the free energy of a reaction, is negative. Therefore, if the temperature and entropy is higher than the enthalpy. If you deduct a higher value from a lower value here, definitely you get a negative answer. So for a spontaneous reaction, the free energy will be very, very low or negative, meaning that it does not require any energy. You don't need to put in a lot of energy for such reaction to occur. The reaction will occur easily, spontaneously. So if a reaction is not spontaneous, it's the other way around. It means that the temperature and the entropy here are very, very low compared to the heat of reaction. So definitely if you deduct a lower value from this value here, maybe you have 10 here, you have 50 here, definitely we get a positive value. So if delta G, which is the free energy, is positive, then the reaction is not spontaneous. It will not occur easily. And so with that knowledge, we should be able to answer as many questions as possible here. And before I continue, I would like to talk quickly on the exothermic and endothermic reaction. Now look at this energy profile diagram. Here represents the reaction pathway, and this is the heat of the reaction in kilojoule per mole. Now when you see this, it means that initially, assuming this is 1, 2, or 10, 20, this is 0, and this is 30. Here, if you trace this value here, you will see that this is the heat of reaction at the end, which is the enthalpy of products. Products will be formed at the end. Then at the beginning, this is the heat of the reactant. It means the enthalpy of reactants. It means at the beginning of a reaction, the heat of reaction is higher at the beginning. The heat of reactants is higher at the beginning, and then heat has been given out, and at the end we have a lower heat, like 20. So what's the quantity of heat given out? That's like 10. And how do we get that? We look at the difference between 30 and 20 here, and that results into the delta H, which is a change in enthalpy, which is the heat of products minus heat of reactant. So in this case now, we can see that the heat of product is lower, let's say 20, and the heat of reactant is 30. This will definitely give us minus 10. So if you see this kind of diagram in which the heat of product is lower than the heat of reactant at the beginning, it means that reaction, the heat there will be negative, and such kind of reaction is an exothermic reaction, a reaction involving the loss of heat to the atmosphere. So we can see that this is the heat change. The quantity of heat that is given off is at this place, delta H. So here as well, we can have the top here is called activated complex. While from here to this side, here is the activation energy. And activation energy is the minimum energy required by reactant particles to form product. The minimum energy required for a reaction to take place is the activation energy. It was processed by a reactant particle. It is from here up here. While the top here is the activated complex, which is an intermediate between the reactants and the product. You know, the reactants attain a certain energy level, which is here, before products start appearing. That is the activated complex. And for an endothermic, so in an exothermic reaction, the heat of reactant is negative. While for an endothermic reaction, the heat of reactant is actually positive. How? Let's look at this illustration. Let's assume this is 10, this is 20, this is 30, Now, looking at this, this is the heat of reactants is 20, and the heat of product, trace it this way, is like 30. So how do we determine the heat change? Just trace the difference here. This is the heat of reactant, heat absorbed. Heat was absorbed there. That's why at the beginning the heat was very low. At the end, the quantity of heat was higher. So if at the beginning, which is the heat of reactant, we have 20, at the end we have 30, it means that the heat change definitely is heat of product minus heat of reactant. So that is 30 minus 20, which is positive 10. So in an endothermic reaction, that heat is absorbed. And you can see here, see the level compared to this level. It is absorbed. That's why we have a higher temperature here, higher enthalpy here. We can see here that the enthalpy change will be positive. So that is for an endothermic reaction, which is a reaction involving the absorption of heat to the atmosphere. And so we are moving on to treating the Jamb questions here.